Hello, everyone, and welcome to the Water Resources Institute Spring Seminar Series, Catamounts, Catalyzing Change. During this semester series, we are highlighting UVM alumni that focus on impactful water work across the nation. The series will dive into their current work as well as how they navigated their path from UVM to their current career. My name is Jacob, and I am a graduate student here at the University of Vermont, and I'm very excited to introduce today's talk by Graham Sexstone entitled Snow Hydrology Research to Improve Water Budget Assessments Across Snow-Dominated Regions. Graham Sexstone is a research hydrologist with the U.S. Geological Survey Colorado Water Science Center in Lakewood, Colorado. He received a BA in geography from the University of Vermont in 2007 and an MS and a Ph.D. in Watershed Science from Colorado State University in 2012 and 2016, respectively. His research focuses on understanding the spatial and temporal variability of snow water resources and how changes in snow processes are linked with changes to water availability. This talk will be about 30 minutes with 15 minutes of Q&A at the end. Please hold your questions until the end. Welcome to our remote guests. If you are joining us via Zoom, you can enter your questions into the chat box at any time during the presentation. I will now turn the floor over to Graham.
Thanks, Jacob. Try to sneak it. All right. Thanks, everyone. Appreciate the invitation, and it's nice to be back in Vermont to give this seminar. I was asked to give a brief overview of my journey from UVM to kind of the current stage in my career. So I'm going to start out by just kind of giving a few overview highlights of the journey along the way. So I completed my BA in geography from the University of Vermont in 2007. And my coursework focus was really on GIS, physical geography, natural resources, and ecology. During my undergraduate time here at UVM, I think it had a lot of valuable opportunities. One that really stands out to me is my time working as a research assistant for Professor Beverly Wemple and also Professor Don Ross. I think, these roles I was kind of served as a field assistant, and I was able to help measure stream chemistry and precipitation patterns on Mount Mansfield, as well as nitrate levels in forest soils across multiple ecosystems. And I think these kind of early research experiences and opportunities really introduced me to field-based hydrology. And to be honest, being paid to work on Mount Mansfield and Camel's Hump was definitely one of the highlights of my undergraduate experience. Another really formative moment for me was being able to participate in a semester-long applied ecology field program in New Zealand. So I got to study abroad in New Zealand for half a year, and I think that further strengthened my skills in field-based environmental science. So after I graduated, I spent another 3 years working here in Vermont, worked for Pioneer Environmental Associates, which later became VHB. And I worked as a water resources scientist. And I think this consulting experience really kind of helped me with some hands-on experience in water supply source evaluations and water quality monitoring and regulatory permitting. Really kind of, I would say this consulting experience helped me to develop my technical, analytical, and field skills, and really helped cement my interests in hydrology. So from there in 2010, I had the opportunity to go back to grad school, and I moved to Fort Collins, Colorado to get my Master's of Science in Watershed Science at Colorado State University. I worked with Professor Stephen Fosnacht, and that's really kind of when I started to focus on the spatial and temporal variability of snowpack properties. And that really shaped my trajectory of research on snow and focusing on mountain water processes. As a master's student, I got to serve as a graduate teaching assistant for a number of courses in watershed processes and physical geography. So leading labs and working with students. It really helps kind of strengthen my technical communication skills and ability to help explain hydrologic concepts. And so when I was finishing up my master's degree at CSU, I was also able to get hired by the USGS in 2012 as a hydrologist. And so I was able to, was fortunate to kind of have support from my advisor at CSU and also from the USGS to kind of work concurrently to get my PhD while also working full time for the USGS. And so I've been at the USGS ever since. I completed my PhD in 2016. And I think ever since I've really been focused on trying to elevate the role of the importance of snow hydrology research in the agency. So this kind of brings me to today's talk, where I'm going to really try to talk about how my research and our team's work in snow monitoring and modeling and remote sensing are helping to improve water resource understanding and decision making in snow-dominated regions. All right, so why do we care about seasonal snow? I like to start off with this slide in most talks that I give. Our seasonal snowpack is really a critical water resource in many regions throughout the world. And from a hydrology's perspective, our snowpack in snow-dominated regions can drive how water moves through a basin and ultimately contributes to stream flow. This is a pretty simplistic graphic highlighting that if we have sort of a high initial soil saturation in the fall, and we have kind of a high snow accumulation or snow water equivalent accumulation, that often translates to a later snowmelt timing and an increased summer stream flow. And then the bottom row is sort of the opposite case, where if we have this low initial soil saturation and a low snow water equivalent accumulation, we often see kind of earlier snowmelt timing and a much lower summer stream flow. And really, there are numerous other factors that also play a big role contributing on why and how snow turns into stream flow. Things like snow sublimation and evapotranspiration are particularly important. But really, the point here is that an accurate characterization of this seasonal snow water reservoir and understanding its complex variability is really important for water availability assessments. So this is a nice graphic highlighting how our snowpack and our stream flow are so tightly coupled in places like the Western US and Colorado. This is showing data from 2011, which was one of the highest snow years on record in northern Colorado, and then subsequently 2012, which was one of the lowest snow years on record until this year happened in Colorado. So you can see in gray is sort of the snow accumulation and melt, and then in blue is sort of the responding stream flow data. So what are the data gaps that we have in our existing snow to flow monitoring networks? The Natural Resource Conservation Service, or NRCS, operates really the most expansive and important snow monitoring network across the Western US. You can see there's snow monitoring data gaps in other snowy regions of the country, particularly in the Northeast. But when we focus in on the Upper Colorado River Basin, and then we sort of plot up where these SNOTEL monitoring stations are positioned elevationally, we see that high elevation alpine areas and then also lower elevation areas with varying land cover types are important environments that we don't typically monitor, and additional snow station observations could benefit remote sensing and modeling. In addition, in the Western US, there's really a need for more kind of natural, unaltered stream flow monitoring in smaller, high elevation catchments that correspond with snow data important for these water cycle component evaluations. So in the USGS, we've been focused on new snow hydrology monitoring activities in the Upper Colorado River Basin. We've done quite a bit of stakeholder outreach that really highlighted snow and stream flow data needs are a huge priority in the Upper Colorado River Basin. And this is a region where, as much as 75% of our stream flow is thought to originate as this seasonal snowpack. So the USGS have been focused on new monitoring research and methods development focused on snow in the Upper Colorado through our Next Generation Water Observing Systems project, or NGWAS. And we've really been focused on three key data types for this project, one being continuous snow mass and energy balance stations, two spatially distributed snow observations and surveys, and then three new streamflow data for water cycle component evaluations. These are just a few photographs highlighting some of our field activities. So I'll start kind of going over some of our continuous snow station monitoring. We have this new research network of snow monitoring stations, really focused on measuring snowpack mass and energy balance variables. Currently have 14, I might call it 15 stations across our study area that really range in elevation and also land cover type. Again, trying to fill in some of these environmental gaps that we have in snow monitoring. So we have two of these sites that we're kind of classifying as our test bed site locations. One shown on the screen here, this is our Ranch Creek site that's in Winter Park, Colorado. And then our second site is co-located with an NRCS SNOTEL station. And these test bed sites were really trying to, provide the infrastructure needed to test a range of new sensors so we can kind of bring redundant sensors online, test new equipment. And these are sites we're really focused on kind of trialing our new technologies and workflows. And then at all of these snow monitoring network sites, we're visiting them in the field during the winter, digging snow pits, completing spatial snow surveys to really try to provide kind of a robust data set for evaluating these new sensor types. So this is a map of our study area. You can kind of see the Upper Colorado River Basin as a whole in blue, and then our watershed of interest for the NGWAS project in black. And then the green circles on this map are our distribution of our new snow network sites. We also show USGS stream gauges in blue, and then the existing NRCS SNOTEL sites in purple on this map. All of these sites are currently collecting data in real time, and data are available in our NWIS database. And then this is kind of the laundry list of the different variables that we're measuring at each of these sites. So a number of snow-specific variables, snow water equivalent, or SWE, is really one of the most important variables of interest. But we're collecting soil moisture and soil temperature, as well as radiation data and meteorological data. So really it's kind of all the variables that you would need for kind of taking a physically based modeling approach of the snowpack. And this is the web page on this slide we have for this project, and you can go to and access all of the data. So as I mentioned, we're doing a lot of field work where we're visiting these sites, digging snow pits, collecting measurements of that snowpack mass, snow water equivalent, snow density, so that we can compare to observations. And so this is a plot highlighting how our station observations of snow depth on the y-axis compares to our observations that we collect manually at the station. You can see snow depth comparisons are really good. When we look at snow density, we see the comparison is reasonable, but certainly not as good as snow depth. And snow density is just a much harder variable to measure, both in a snow pit as well as through a station. But when we look at kind of the comparison of SWE, we see that relation is pretty strong between our stations and our snow pit observations. We can also compare some of these new stations to existing SNOTEL monitoring sites. And so the photograph on the screen on the top right in the forested environment is a typical SNOTEL station. So our SNOTEL sites are generally in forested areas, but they're in small clearings in the forest. So they're very sheltered environments that kind of limit the exposure to wind. And then on the top right is a photograph of one of our alpine high elevation sites. And so you can kind of see the difference of environment type of these monitoring stations. And so they're actually a few miles apart from each other, but it's really a difference in over 1,000 feet of elevation between the sites. So this plot is highlighting in the dashed blue line is a SNOTEL monitoring station, and then the dark blue line is our nearby alpine monitoring station. And you can see this is the past 3 years of data, and a few things that jump out is just really the timing of snowmelt at this higher elevation alpine area is much later in the year compared to SNOTEL. And then we also see some dips in the signal in the darker blue line that really represent kind of losses from blowing snow redistribution and sublimation that we see at these alpine sites. I'm also plotting blowing snow fluxes in green and computed sublimation losses in orange from this alpine site over these past 3 years. You'll notice sort of the most recent year, 2026, on this plot highlights how there's a lot less snow in these alpine areas compared to the SNOTEL. Although the SNOTEL site's also showing a lot less than previous years, the difference between these years is pretty substantial. And we had a very major snow drought this year in the Western US. And some of these differences that we can key in on, for instance, there being a lot less snow in high alpine areas, I think is pretty important for kind of painting the picture of that spatial context of our snow distributions. We've also been working a lot on, collecting spatially distributed snow observations, both with, traditional techniques of using a snow probe and snow cores. And we've also been doing a lot of work using UAS observations, using LiDAR, radar, and photogrammetry. These are some plots just highlighting the distribution of snow depth that we're measuring with spatial surveys compared to the nearby stations, which are the points shown in purple and red on those box plots. So we're seeing that actually the distribution of snow around this particular site is underestimated from the station observation compared to its surroundings. And these are the types of data sets that we're, leveraging to help support some of our modeling evaluations we're doing of distributed snowpack. This is an example of some of those drone-based surveys that we've been doing. The image on the bottom left is a software-defined radar instrument that we've been using for monitoring snow distribution. And then the image to the right of that is a LiDAR-based UAS sensor. And so we've been flying this study area at Berthoud Pass quite a bit, which is kind of an area subalpine to alpine transition zone around one of our stations. And then the map on the right is highlighting the snow depth distribution from LiDAR. I can play this little video that we're measuring. And so you can see the darker colors and the purples are the deeper snow, and then the lighter blues and whites are more shallow snow. And you can see how much of an influence the forest canopy has on this snow distribution and how much variation we see in the alpine areas. And so this is just kind of highlighting this complex variability that we're trying to represent. We've also been working quite a bit with airborne snow observatories, or ASO. And so this is an aircraft or airplane-based LiDAR survey where we measure surface elevations when there's snow on the ground and then when there's not. And we can difference those and get, through modeled snow density and measured snow depth, we can get snow water equivalent estimates over larger, basin extents. And so this is an example on the right of the snow water equivalent product from airborne snow observatories over, a pretty large extent over a few different large watersheds. And so this is these data sets are really pretty important for serving as foundational science data sets for us evaluating different ground-based, remotely sensed, and modeling methods. And at the same time, a lot of our new observations are being used by ASO to evaluate their products. That being said, these data sets are really snapshots in time. So we have to kind of leverage these spatial observations with other techniques. And that kind of brings me to a lot of our focus being on, a snow hydrology modeling approach. We're really hoping to kind of improve snow modeling capabilities, using the range of observations that I've highlighted here, both ground-based and remotely sensed. And then as kind of shown on this graphic, we're hoping that, observations can help, inform the modeling, but at the same time, the modeling can help in turn inform maybe where we need additional observations for the future. So our goals with the modeling approach is one, really investigating some of the physical mechanisms that are influencing the water budget in these snow-dominated regions, scaling, snow modeling applications to larger regional extents and snow regimes, and then developing some real-time capabilities with this model so that we can use this information in more of a real-time water forecasting context. So the model we've primarily been using for this work is called Snow Model. It's a spatially distributed process-based snow evolution model. It's able to simulate really the important processes and interactions that drive this snow variability that I've been highlighting at pretty fine scales of interest. It's able to represent snow processes in alpine and tundra environments, things like wind redistribution of snow, as well as processes important in forested environments such as canopy interception and sublimation. And it requires, spatially varying fields of elevation, land cover, and meteorological forcing data sets. So I'm going to highlight just kind of a few studies that we've completed recently using this modeling framework. The first here being focused on snow sublimation. So sublimation it's analogous to evaporation. It's essentially the loss of water directly from the snowpack from solid to vapor. And this is actually work I completed as part of my Ph.D. research. So we combined eddy covariance observations with water balance measurements and snow model to try to investigate, sublimation and its importance in these mountainous environments in Colorado. And our results highlighted that, our simulated sublimation across our spatially distributed study area was equivalent to about 28% of winter precipitation on average. And we also highlighted that the highest relative sublimation fluxes tended to occur in the lowest snow years. So this is a process that potentially becomes even more important in low snow years like we've had out in Colorado this year. We also saw spatially how this process was much more important in alpine areas as well as in specifically forested areas, whereas openings in the forest below tree line tended to have less sublimation losses. So it's really, the results also particularly highlighted forested areas accounting for the most sublimation fluxes because we geographically have, more forested area in this snow-dominated region than other environment types. We've completed a recent study looking at some high-resolution estimates of both historical and future snow water equivalent and snowmelt runoff. So we kind of using snow model, did a historical and sort of future climate experiment to see, across elevational gradients, how our snowpack is expected to change. And so we saw that peak snow water equivalent was lower, quite a bit lower for the lowest elevations, but also lower at middle elevations in a kind of a future climate scenario. Whereas the highest elevations remained relatively unchanged. Whereas the date of the peak snowpack amount was uniformly earlier across all elevations in this experiment by as much as 17 to 23 days. And one of the results here really highlights that, currently this unmonitored high elevation snow is going to represent an even greater fraction of our total snowpack reservoir in this future climate scenario. We also looked at surface water input, or you can essentially think of it as snowmelt input. And we saw the peaks in this. Snowmelt input was higher across all elevations. And then the peak sweep timing really shifted earlier, as highlighted by this plot on the right, showing kind of the difference in surface water input across a number of elevations. We've also been doing quite a bit of work recently looking at how we can maybe do a better job of representing snow modeling in forested environments. Our forests are highly complex, and snow distributions within these forests are strongly influenced by kind of the structure and makeup of those forests. So we've been using LiDAR-derived forest canopy structure data sets combined with spatial snow surveys to really try to evaluate some of this forest snow variability. The plot on the right is highlighting 2 years of snow-tell observations shown in the lines. And then the symbols represent manual snow surveys that we completed in this study area over different canopy types. So we looked at kind of north-facing edges and south-facing edges of the canopy gaps themselves, as well as the interior forest. And you can see the spread in that data set is almost as great as the historical spread in the 30-year record of the SNOWTEL data set. So kind of really highlighting the importance of canopy structure in some of these observations. So we've been developing kind of an empirical parameterization approach to try to better represent these different forest canopy environments within snow model. And we also have been working with Anna Gruens, who is here at UVM, trying to apply some of this snow modeling technique in Vermont. And so Anna's done a bunch of tremendous work setting up snow model using historical observations as well as new observations from the Summit to Shore network to really try to evaluate how this type of snow modeling approach can work here in Vermont. And I think this research is really poised to help partners better understand the sensitivity of snowpacks in the Northeast to changing climate conditions. And one thing that really we highlighted in this work was the need to kind of change the parameterization in the model for how the model represents meltwater moving through the snowpack. In an environment like Vermont, where we have a lot more kind of midwinter melting, and it's potentially very susceptible to rain on snow events, that was an important change that we were able to implement in this model application. So we've also been doing quite a bit of work focused on, how can we take this modeling approach, apply it in real time, and what are the data sets that can really maybe help inform some of this real-time modeling. So we've been using MODIS and Landsat remotely sent snow cover area data to help calibrate our snow model historically, but also constrain snow estimates that we can make in real time. This is a map of mean annual snow cover persistence from Landsat. So you can think of over a 30-year period on a grid by grid basis, how many days per year do we typically have snow on the ground as observed by Landsat? And this data set over a 30-year mean condition can actually provide a lot of information on snow patterns across the landscape. So we've been able to utilize this to improve some of our fine resolution snow modeling approaches in near real time. This is a map highlighting a few of the domains that we're currently running with this real-time approach in Colorado. And we're also developing a few domains currently in California for this type of application. And so these are some results we recently published highlighting kind of this framework we're using, the snow persistence and remote sensing observations to help calibrate and constrain snow model. This is sort of some of the results from our initial calibrated snow model for a few different watersheds in Colorado. And then this post-processing technique where we're constraining the outputs to the observed fine resolution remote sensing from Landsat and Sentinel, and how that kind of can change some of the snow water equivalent estimates. And then we show how that compares to the ASO data sets. So that's sort of, basin-wide surveys of using LiDAR. And you can see how kind of the comparisons of the spatial patterns are actually quite good here, where our models with this approach can capture a lot of the locations of these deeper snowdrifts and alpine areas. And the approach of using the snow cover extent to constrain the model helps quite a bit at lower elevations near snow line. We see less improvement at sort of the highest elevations using this approach, though. So, yeah, in summary, I just want to highlight that the USGS is conducting, new snow hydrology monitoring that we hope can provide high quality, publicly available spatial temporal data, crucial for modeling and remote sensing evaluations. This is a web page you can check out that has access to a lot of these data sets I've been describing. We have ongoing research that is really focused on improving some of these real-time estimation techniques of SWE and snowmelt through process-based snow modeling combined with plot to basin scale observations. And we hope this type of snow monitoring and modeling research can be used to better understand runoff efficiency and support water availability assessments and forecasting. So thanks for your time. I do want to acknowledge a number of co-authors that shown on the screen. This is definitely a team effort, and I have a great team working with me on this. So thanks very much. Chris.
You don't have your slide about how you're assessing the model estimations. I didn't quite understand. I mean, I think that
This one?
yeah, there.
This one? Yeah.
So you're doing these, gathering data from various means, LiDAR, distributed sensors, etc.
Mhm.
You're then using the snow model, is that the correct name?
Yeah.
Really creative name.
The snow model.
And then, you're actually doing manual snow courses.
Mhm. For this particular effort, we had a small study area where we're doing quite a number of observations on the ground.
Throughout the entire area that you're doing the estimate with the snow model, because it's, I mean, it sounds like you're proposing to do this in a macro, like let's say at a basic scale.
Yeah.
But you're not doing snow courses.
No.
Throughout that entire basin.
No. So you can think of the 14 monitoring sites that I showed. A lot of those stations were doing monitoring around them in kind of adjacent areas, and we're collecting a lot of data from those kind of plot scale observations. And then the hope is the modeling is the link that then we can, make improvements in the model and run that over basin scale assessments. So we do have some observations from the airborne LiDAR over large regional or basin extents, but really the modeling is the link of how we can do this over larger areas.
I guess my question is, are you evaluating from what the models?
Yeah. Yes.
Through these.
Yes, through observations at these kind of more plot scale study areas, but also we're evaluating it with ASO over basin scale. So like this plot is a comparison to like the first two columns are the model estimates, and then the ASO on the right is an observation base estimate.
And the inputs, so then the inputs to the model are just your ground-based sensors.
The inputs to the model are just the distributed meteorology, not the ground-based sensors. The ground-based sensors can be used in the model to like assimilate, but like the model doesn't need snow water equivalent. It just needs precipitation, wind direction, wind speed, air temperature, humidity. Does that make sense?
Yeah.
Sure.
Is the story, I was noticing when you were showing this before, how far ASO is off at the highest elevations. Is the idea that you don't have many elevations up in that, or observations up in the outline, and then when you fly the ASO surveys, you're seeing there's not much snow there.
Yeah, I mean, I think that we have more observations now through this project, but there's still only some point data. And I think what those stations can help us do is have better, information about blowing snow, sublimation, but there's still, I mean, these are large domains, these are big watersheds, and the complexities in the Alpine in Colorado are substantial. So the fact that their ASO is higher than the model in those particular years is likely that the model wasn't blowing enough snow into some of these deeper snow drifts, is my guess. Could be a lot of reasons for it, but I guess the takeaway is if you look at the SWE average over the basins in these plots, they're pretty close to ASO compared to most modeling efforts. Yeah, so and we're making improvements, but certainly I think, it's just a challenge trying to represent snow in these real complex environments. Hey.
As we sit and talk about, the distributed meteorology as but
Mhm.
have you had done any work where I'm curious if you've had to make adjustments to meteorological data sets to use them, or looked at using multiple data sets or comparing them?
Yeah. Yeah. I would say this precipitation especially is the biggest uncertainty in snow modeling. Wind is also a really important parameter and is often underestimated with these distributed data sets. So yeah, we generally have to do some bias correcting of meteorological forcing, especially in these mountainous regions. And so we're using station data for making some of those comparisons, but we also use, snow observations as another way to make really bias corrections to the meteorological forcing. But yeah, I think the Met forcing data sets are uncertain and also like a really key piece to the accuracy of the model. So
My question was similar to that, because I noticed in your list, precipitation was the TBD.
right.
Similar challenges in Colorado as we have near tree line on Mount Mansfield, in that even if you have a shielded precip gauge, it could end up being sort of a best guess.
Right.
Like now at Ridge in Colorado, for example, the highest elevation precip sensor there had a ton of overcatch.
Right.
And overcatch was occurring during blowing snow.
Mhm.
So it was basically like imagining a whole bunch of precipitation that
Right.
didn't occur. So I'm curious, given the priorities of NGWAS, if you all have measuring precip in mountain environments as a objective or wish list.
I would say wish list, but I'm especially in the Alpine, it's sort of been like, I don't know if it's worth even trying because of the undercatch issue or overcatch issue. I've been interested in trying to take some approaches on how we can use some of the snow data sets to maybe like come up with like a time series of precipitation. So we haven't really done it yet. We do have some kind of radar-based precip sensors, but haven't really been focused on them yet. So it's on the list, but like I think initially it was on the priority list for me, and then it became clear that all these other things are really hard too, and it's gonna push it off a few years. So yeah, I mean, I think measuring precipitation, especially in the winter, is really important. And it almost needs like a specific focus. So yeah.
Maybe an avenue for future work.
Right. Yeah. Yeah, I don't want to like understate how important it is. It's also like I feel like I could only do so much with setting up all those stations. And so
Yeah, and well, sublimation was your other target, just
right.
yeah,
Yeah.
massive unknown.
Yep. Yep. Scott.
You mentioned a real-time application like constraining snow model with the satellite data.
Yeah.
Is there anything you're planning to do to like do a retrospective run of snow model, like over the whole kind of upper Colorado? Or is that feasible like, with that kind of setup?
Yeah, it's a good question. I think it is feasible. So for these approaches, we've been working with Bureau of Reclamation and doing kind of retrospective runs to calibrate the model. And then we've really only been applying, so we are kind of, providing that calibrated historic run, but then kind of using the remote sensing to constrain it. We've only been kind of taking it into the real time forward. I think it is feasible to some degree. It's more about like availability of remote sensing data sets. So MODIS, for instance, kind of began in 2000, so we couldn't really go using that data set earlier. There are Landsat data sets, but it's kind of like we're using Sentinel a lot, which is also more recent. So we would run into more and more data limitations as we went back. But I think it is feasible to try to do some of that work. We just haven't really approached it yet. Thanks. Beverly?
Yeah. Two-part question. I think in one of your slides, I saw some snow scale. And when we were designing the Sum to Shore project, I'm sure it was you who was giving us advice on what to use.
Yeah, right. Sorry.
Use what you might do over or do differently. And the other question is, what have you learned from co-locating some of your sites near the Snowtail sites? I think that one Snowtail comparison you showed was like a site here to a site higher.
Yeah.
What about
Yeah. So the photograph on the top right of this screen is Berthoud Pass, and that one we have a snow scale right next to a snow pillow. And they compare really pretty well. So it's that comparison has given me more confidence. I think snow pillows are great and work really well. The challenge with snow pillows is just sort of the environmental concern of if you would be allowed to put out new snow pillows. And so I think snow scales are nice for that reason. Like you don't have to disturb the ground and you can just kind of lay them out. And overall, I think we've seen pretty strong performance with them. They have a smaller surface area for how they measure, and I think bridging of snow can become an issue. And so really like same thing for snow pillows, but snow pillows have a bigger surface area. And so they kind of can help, deal with that issue by having that bigger surface area. But we have seen, particularly in alpine areas where we get some like hard wind slabs and things like that, that can create some bridging, that can create challenges. But I feel like it's also, there's a lot of it's like real dynamics that are happening that don't look like a typical SNOTEL time series, which I think have been informative. People may look at them and be like, that looks wrong, but it's like, well, it's also just not what you're used to seeing because we don't typically monitor snow in these environments. So I think overall I think the scales work pretty well. I think in some places like the Alpine, though, their non-contact approaches might work better if it's the right conditions. So there's a gamma radiation sensor that's, more of a non-contact and has a bigger footprint. And if the snow is not too deep, I think it can work pretty well. It's like when it gets too deep, it doesn't work. So what I've learned for SWE specifically is that it seems to be a range of sensor types that might work based on the environment that you're in. But overall, I think most of the sensors have performed pretty well for our network. Infrastructure has been pretty robust. There's some things that are harder to evaluate, like blowing snow particle flux. We have these sensors and they seem to work pretty good. They give us realistic numbers. When the wind blows really hard, we see blowing snow, but it's really hard to be like, how accurate is this? There's, same with like the liquid water content sensor in the snowpack. In some ways, the only way to evaluate some of these sensors is by modeling the data. And so it's a little counterintuitive. So that's been a challenge. How do I write this up as a technique to evaluate? So, Blaine.
This slide reminded me of a question I had. Can you talk about the importance of measuring snow density?
Yeah.
Because you measure speed very well, the snow depth very, very well. Why you need to measure density?
Yeah, it's a great question. And I don't know if I fully explained this slide well enough so you can imagine the top right picture where we have our kind of our station. It's measuring snow depth, and we're measuring snow depth like right under the sensor. But the SWE plate is also where that snow depth is being measured, but we can't dig a snow pit right where the sensor is measuring because it's a destructive technique. And our snowpack varies at such short distances that the snow pit that we dug in this photograph is likely, a different depth than what we're measuring at the station. So that comparison of the station SWE is actually the snow pit density, but then we're applying the station depth to that density. So it's really kind of taking the density, and we see a stronger relation there. But I think measuring the snow density is really like the only way that we're also measuring SWE. So it's an important thing to measure for, multiple reasons. But I think a lot less is also been focused on density variations in modeling efforts and observational efforts. So apart from, the sensor itself, we also are trying to do more spatially distributed density to get a better handle on how that does vary, and if the model, we can improve the snow density modeling itself as well. Because there's a lot of focus on LiDAR measurements, but to get SWE, we're modeling the snow density. Yeah. And I think that gets glossed over a lot as like, oh yeah, we'll just model the density doesn't vary, but it really does. So
Now,
Yeah,
is
Chris.
that variability there? I mean, are you taking, no, are you taking?
no, we're digging snow pits.
Oh.
Yeah. which has uncertainty in itself. You know, measuring a snow pit is not a straightforward task. I mean, I think our team we have a very, you know, strict protocol and I think are pretty good at it, but it's, you know, the snow varies over really short scale, so you can just have uncertainty in your snow pit.
Right, even if
Yeah.
the reading is accurate.
Right.
So,
Yeah.
though that variability might not be due to problems with sensors.
Right. Very much may just be natural variation. Yeah.
After you dig a pit, you fill it back in.
hmm
Yeah.
Try to. You can never fully fill it back in
Right.
the way snow behaves. But yeah, it's kind of, we try to, I mean, for one, you don't want a skier falling into it or an animal falling into it. But two, we don't, especially when they're near our stations, you don't want it to kind of, you know, mess with the aerodynamics of the area. So
Right.
Yeah.
And then so how far do you usually try and get from a previous pit to the
yeah, it depends on the site, but often we'll, like in an area like this where there's not a ton of room to be nearby, you know, we'll actually sort of try to keep the front of the pit wall undisturbed, throw the snow back, try to fill it back in, and then kind of mark that front of that pit wall, and then we could just sort of step forward, you know, half a meter, and next time dig the pit right there. But some sites we'll just dig them in different areas because we have tons of room to work with. Yeah.
Frequency that you do these pits?
For this network, we're trying to get to these sites 2 or 3 times a winter. So generally we're kind of like early accumulation, peak accumulation, and sometime in the middle of the snow melt season. And that is a lot of that is driven by trying to capture variation in the surrounding snow because we do these snow surveys every time we go. You know, trying to understand if there's sort of non-uniform melting going on that really changes that snow distribution during the melt season. So, yep.
Can you ever gather data from like the routine avalanche forecasters that maybe go out and also dig pits? Like,
Yeah.
are there data sharing that can talk into that?
Yeah, there's a really cool project. It's called Community Snow Observations, and they have created an app where you can, like, if you're out in the field, even if you're just like skiing for fun, you bring a depth probe and you take a measurement, you can upload that to Community Snow Observations. And those data can be assimilated into snow model. Like that's actually the point of that initial project that they set up. More so snow depth because most forecasters for avalanche don't measure snow density. You know, they'll measure hardness, but it's not kind of a direct correlation, and they often don't dig a snow pit to the ground. They're like, we want to dig a meter to the weak layer, but we don't want to measure the entire snowpack. So, but snow depth is really very valuable, especially in some of those higher elevation areas. Thanks. Yeah.
Question. I'm interested in like the connection to sort of operational applications of this.
Yeah.
Forecasting.
Mhm.
Can you talk about like what goes into providing stream flow forecasts?
Yeah.
Reservoir operations or like agriculture.
Right.
How does this or how would you like this to inform that?
Yeah.
That there's a space and
Yep.
And do you ever like compare these to just kind of simple statistical regression, like
Mhm.
we have our snow measurements,
Yeah.
just some statistics to predict
Yeah.
stream flow.
Yep.
Or like looking to see how it compares.
Yeah. So I'll answer the last part first.
And what's your favorite color?
Green. The I got that one right.
Yeah.
So have done some, you know, comparisons of like, say, here's the snow tail site and here's the stream flow. We create like a linear regression between those two. And that's kind of what a lot of forecasting initially was developed based on that. And like that's why SNOTEL sites were set up as kind of index sites. And so we've taken some of the snow modeling work and taken the, watershed wide average SWE on April 1st and also compared. Kind of depends on the area, but we have seen for Lockvale, for instance, which Lockvale, we've seen some improvements, but it's not like a one-to-one thing. We wouldn't really expect it to be because there's other hydrology going on. But we have seen some improvements of kind of like the modeled estimate of April 1st compared to stream flow, compared to kind of the station-based estimate. Generally, that relation improves through time. So you look at the May 1st, it tends to be better. And then if you look at sort of the cumulative snowmelt from the model, it's even better. So I think a lot of the uncertainty in those relations is just the spring, weather conditions that we get. So, I mean, that is a lot of that historical statistical framework is what water resources forecasting, water supply forecasting was built on. Using SNOTEL sites as index locations and developing regressions based on observed stream flow. A lot of those relations aren't holding up because of changing climate conditions. And at the same time, forecasting agencies are certainly using more sophisticated techniques nowadays. So the NRCS, for instance, is using they're still using forms of regression, but they're using a lot more predictor variables and they're bringing in more sophisticated statistical techniques. There's also a lot of work done by the river forecast centers, and they use more of conceptual modeling tools. So they use kind of SNO 17 and SAC SMA models. But they're still highly calibrated based on observations. And so they need kind of this historical record of data to calibrate those models. We generally need like 20 years of data. So there's this big challenge of how can new observations or new modeling really fit in with those frameworks. And I think that's really an active area of research that we need to pursue because we want these types of data sets to be impactful and so I can see a lot of value. We are like in some of these real-time applications I'm mentioning, we are kind of working with Bureau of Reclamation directly, and what they're doing is they're running their SAC SMA model in SNO 17, and then we're running the snow model, and they're taking those values and they're kind of nudging their conceptual model based on some of the outputs from snow model. So that's one approach. But I think, we need to figure out how can, particularly data sets. I mean, I think because we need more ground observations to base things in reality. And then how can those be pulled directly into some of these water supply forecasting techniques? So thanks for that good question.
More data.
More data.
Okay, that brings us to it. And the one who's doing the last thing here. When the Alumni Association, when we were doing this series featuring our alumni, they brought over bags of UVM swag, and we're gonna stuff the bag with WRIs.
Nice.
So thank you for coming back.
Thank you.
Wishing that.
Yeah.